get started. So cool. How's everybody doing so far? Was the last lecture helpful? Okay, cool. So from today, we're gonna formally enter the next module where we will start talking about how we understand and model protein structures instead of just sequences. So we're gonna mostly cover like AlphaFold and AlphaFold 2 and extension AlphaFold 3, as well as some concepts that are important to understand the protein folding tasks and relative data. And but before that, since we kind of spent a really short time on equivariant deep learning, so I noticed that there might be some concept that were not explained clearly before. So I'll try to get to a little bit more about the group and representation theory and the tensor product. So maybe to help you better understand the last lectures. So don't think too hard. I think this part is just totally additional that to help you better understand the previous talks. But I mean it's something that as Simon mentioned, that something that's powerful because these operators are designed to be equivariant, but at the same time, they're not needed if you have enough data. So you can do it in a fully approximated equivariant fashion. But there are certain concepts that has been mentioned a lot in the past talk. For example, like groups and representations. So groups are in a high level. You can consider this as kind of the notation of operators, or all kind of possible operators related to certain types of operation. For example, rotation. All the possible rotations can be a group. And the concept of group is mainly defined by how these operators can compose together through multiplication rules. And the groups is operators, and then you need to use the operators on certain space. So there's also vector space that are related to group, and how the groups modify the representations in the vector space is related to the representation theory. So this is you don't have to understand all of that, but just saying that a very important property of a group is that for example, each of the elements you can consider it as an operator, and each elements in the set, where each one operator, we equip them with a product, which shows how two different elements in the same group compose it. So the most important property of the group is associated with this product, where basically if you have two elements in this group, they should be associated. They can be associated with this product, so it is kind of like multiplication, and you could exchange the order of how you associate them. And there are additional rules that basically usually you need to have an identity element, such that when you apply this dot product with another element, it will equal to itself. And then usually also requires some inverse element. So ideally you could possibly generate the other element with this good group product operations. So there are very common, very common groups that involved in our geometric deep learning are like translation groups, where apparently can prove that this composition rule, associated rule, is true. And notably, there's also roto translation group, which we call SE. The 2 here means it's a 2D space, but in 3D space we have SE3, where you have a chained, basically a chained translation and rotation operation. So that inside the SE3 group, the operators are associated with both a translation and a rotation. And you can also prove that this set of chained operators is a group because it has this associated property, and you can also look for the identity and the inverse. So representation is these are very mathematical definitions, but in a high level you can understand representation as a type of object in the vector space. And how this object respond to the group action. And the different types of representation, different types of representation will respond slightly differently to the same group of actions for the same group. So you can consider this as kind of reflection of what the group action means in the vector space, right? So why I call it homomorphism is that we make sure that with these representation rules, the transformation you observe in this vector space also fulfill the same structure as your group. So this kind of dot product structure remain the same in this realization in the real vector space. So in terms of notation, you'll see a lot of time a vector space is noted by V, and the group the set of operators denoted by G, and representation is basically a mapping from G on X on V to a V. So we can see that D of G is a V to V function where you apply something within the group and you observe change in the vector space. So that's kind of how this operation is realized. This group is realized in the real vector space. And again, it has to fulfill the same composition rule to make sure it's a representation of this group. I mean, the concept is a little bit abstract, but you can think of representation as data type, Simon mentioned. So for example, for this group, this 9-dimensional space, we can say the first, we can call define a scalar representation. For example, the top 3 elements, we know that these are scalars, so that for the SC3 group or rotation group, we mainly talk about rotation here because translation can be handled easily by centering your data at the center of mass 0, so you kind of don't need to care about the translation. So mostly we talk about rotation. So for the scalar type of representation, right? We later call it the tensor order or rank of tensor. So this is the rank 0 tensor or order 0 tensors. We define the representation rule to be if you apply the group over the scalars, they remain the same. And we can also define a vector type, which is order 1 tensor, where when you apply rotation to these vectors, it will be rotated correspondingly by doing the rotation matrix multiplication. And you can also say these two are independent tensors and they should be transformed independently. Maybe one of them is coordinated the velocity and the other is force. And I define that, I know that these are 2 different tensor of the same type. Both are vector type and they transform independently. So if we kind of write it up as if you apply a rotation group to these 3 representations, right, you could write out how you realize it in the vector space, which the scalar will just remain the same, so you multiply it with identity matrix, and the vectors will rotate with this rotation multiplication, with basically a matrix multiplication. Any questions so far?
That matrix is supposed to be a rotation matrix then?
Yeah, the R is the specific rotation matrix corresponding to that element G in the rotation group. And A4 prime, A prime 4, 5, 6 are the representation. After you apply this to a vector, how it responds. The response. Basically, the D representation is mapping from 4, 5, 6 to prime 4, prime 5, prime 6. So these are the most commonly seen tensors, but you can see that these are not yet powerful enough to represent rotations yet. So there's sorry, this should be rank 2 tensor, not rank 2. I think what Simon mentioned last time is there's a new type of tensor beyond these 2 tensors, and actually there are unlimited types of tensors. You can gradually increase the order, but there's if you increase order by 1, we get this 3 by 3 matrix, where the concept of matrix is we can consider that as a new type of tensor, and the rotation, the rotation group over the matrix, when you apply it to this representation, it will be transformed in this way. So basically kind of extending what we know for scalar vector to a new a new order, new dimension, and all the matrices are related by this function if you apply the rotation group to this tensor. So all of them are tensors, but usually when people say like tensor or tensor product, they kind of give you example of high order tensors. But actually all of them can be called tensors, but yeah. But people usually you don't use the word tensors because there are like very commonly appearing types called like scalar, vector, and matrix. But you can understand all of them in the framework of tensors. All right, so equivariance, I think Simon defined it last time, but this is a more like formally defined definition where you have these representation groups, right? Like representations, these defined for certain, like rotations, translation groups that maps you from one vector space to the other outcome in our vector space. What is this saying is that for the same group, if you apply the transformation on the input space, and map it with the function f, which can be like a neural network or the function that you're learning. Where you land it is the same as if you apply the function on your vector space first and then apply the group. So this is what we call equivariance. So it's kind of like permutation is another example, like whether you permute input and get output, or you first apply the function and then you conduct the permutation on the outcome. It ended up being the same. So all of these equivariant networks by design, not the like local frame or global frame based network, because like there are different types of equivariant architectures, and actually the AlphaFold that we're going to talk about today does not belong to this type of equivariant architectures. But I think in general, like the very powerful equivariance network by design usually basically try to come up with the function f with neural networks and message passing, such that at the end your network like preserve these equivariance with respect to the roto translation group, most of the time rotation group. So how we're going to make these functions, right? There are very common way of making up equivariant functions. First two are pretty straightforward. Like it is any linear combination of the equivariant function are equivariant, and the composition of equivariant functions are also equivariant. But the last one is a little bit more abstract, where the tensor product of two equivariant function outcome is also equivariant. And by doing this tensor product, you're also able to create tensors with higher orders. So this is kind of a straightforward like Cartesian space tensor product where you kind of imagine it as some kind of element-wise multiplication. So the good property of this is if you apply a transformation with G on each of them, the outcome of the tensor product will be also equivariant to these G that's transformed to these two tensors separately. So the upside of this is you get a very nicely big outcome that's equivariant. But the downside is like it's kind of exploding dimension of the representation that it's needed. So if you do this kind of Cartesian type of tensor product, it would just explode exponentially, which could be a problem in machine learning, because we kind of want to control like the space that we conduct this operation. So there comes kind of what they call reducible representation. So the concept is a little bit abstract, but basically it's a definition that if you have this vector or tensor, and we'll say this representation is reducible if you can find a subspace of that representation, such that over that subspace in that vector space is also representation. So in this example, like the kind of the three irreducible representation that we can find is this kind of like dot product, which gives you kind of a scalar-like type. And you can also find this anti-symmetric part of the matrix, which is you can observe like you only need three entries to in this representation, and these three representations, they are all you can prove that each of them is also representation, but they are of significantly lower dimensions. and the three of them together will basically span all the degree of freedom of the original tensor, the 3x3 tensors. So the good thing about these irreducible representations is, well, there are specific defined way of doing multiplications between the irreducible representations, such that they will generate higher order or lower order irreducible representations, and those can be in the much lower dimensions than the Cartesian tensor product. So this is kind of one way of like, this is one example of finding the subspace, but effectively, like, you could define a very commonly used set of irreducible representations called spherical harmonics. So we can consider this as basically a change of base to your original vector space. So you can empirically, like, I think in physics, people find these particular spherical harmonics as one set of irreducible tensors, which are irreducible representations, which has very good correspondence with, like, functions over the spheres. So they call it, like, spherical harmonics. And the rule of these irreducible tensor is that for each order in this tensor, like L, the dimension of the irreducible tensor is 2L plus 1. So it's like 1, 3, 5, and you can expand it like 7 going forward. And and this also have, like, good correspondence with the Cartesian tensor. We know, like, you can call L0 means basically equivalent to, like, scalar, and L1 equals kind of like vectors. So this is kind of the mathematical formulation for spherical harmonics, but you don't have to memorize that, because the neural net architectures are defined in the way that it does this basis transformation, the change of basis from a Cartesian tensor to the harmonic tensor already with certain linear operations. So basically, this is what I think Simon mean last time, like, where you basically have a matrix where you could try to decompose it into, you can reduce it into smaller, like, irreducible component, and you could change the basis into, like, the spherical harmonics, and at the end you get this reordered, tensors that are, like, ordered by their tensor order from 0. So in this big tensor, Cartesian tensor, you have, like, 3 irreducible tensor from order 0, 1 to 2. And the good thing is, if you split it up in this, break it up into irreducible representations, we do a product between this and another tensor, we know how we can, for each pair of the orders, we know the rules of how to combine them and generate a new tensor that can also be represented by a set of irreducible representations. So basically, instead of, like, exponentially, like, blowing up your space, you have this, like, shared component maintained at each layer, and as you go deeper and deeper, it also increases the depths of like, basically the order of the tensors you can get in a kind of, like, a linear order of growth. But a lot of time we don't care too much about, like, really high order tensors. So you could consider, like, the order of 2 is kind of good for rotation, actually, like, to represent rotations, and you could go, like, up to, like, 4, 5, 6, or there are neural networks that go to, like, hundreds of orders that Simon mentioned, but that's usually just needed for, like, really complex, like, quantum physics or simulations. So for a lot of our tasks, we, like, even order of 2 is kind of good. Question?
Is there any other basis for spherical representation, like not harmonic? Is there other options?
I don't think so. I think like, we call it spherical tensors because it's kind of it correlates well with the function in spheres. So these are kind of very well-known, well-used tensors that also have, like, kind of relationship with the physical meaning in, like, for example, electron density in physics. So I feel like maybe there, so to be honest, I'm not like an expert in this particular domain, so I feel like there might be other way of decomposing the basis, but to me, like most of the time, this is already like very powerful, and it corresponds to the actual like harmonics, like electron density functions that we use in the real physical space.
Yeah, and question two, it is hard to imagine how like a 3D shape is composed by the harmonics. Can you give me some example? Like a 3D shape is decomposed by the harmonics.
So this is not a shape. This is rather how you preserve the rotation or angular moment of a point in space. So it's not just the position, which is the shape, but also like relative, like the vectors defined with respect to the geometries. And there's also like, so if you just need to remember, like if you just need the position, you only need a vector, that's enough. So it's because we want to represent like angular momentum. And for angular momentum, you cannot represent it with just L1. You need L2. And for even harder or like higher order measurements that related to geometries and symmetries, you need the higher order tensors to describe them.
Okay, so this basis can only be used to represent symmetric operations, but not like asymmetric shape.
Symmetric shape. So the symmetric is defined with respect to the operations, with like the group operations. So the shape, whether the shape is oriented this way or this way, their corresponding geometric measures should be changing like correspondingly to these rotations and translations. So this is the symmetry that we mean. It does not mean the 3D shape itself is symmetric. Yeah, I hope this explains it. But the symmetry is not defined in the 3D space. It's defined with respect to this group actions. Cool. So this is kind of the rule of how you can decompose the tensor product if you have two irreducible representations. So basically, the simple rule is like if you combine two irreducible representation of two order, like one have order L1, the other have L2, then you then the outer product, so the tensor product of these two will give you will generate new tensors with the order from L1 minus L2 to L1 plus L2. So an example here is if you do tensor product between order 2 and order 1, then you will be able to generate irreducible representations with the same basis of order 1, 2, and 3, and you just concatenate them together, and that will be the outcome of the tensor product. So in this way, you're computing it with kind of this irreducible component, which can be capped and reused to generate irreducible component of higher order without expanding the space exponentially. And so this is kind of if you write it out in kind of in a matrix expression is like a bilinear operator combining tensors where there are coefficients that take charge of the base conversion, like the base, the change of base from your Cartesian tensor to reducible tensors. And you can also add weights to the tensor product, where the weights, there are particular types of weights that kind of are invariant to like the order of the angular moment that's involved, so you could safely multiply it to the tensor product. So this is one very complex but very expressive geometric deep learning architecture called tensor field network. And the message passing deployed in this tensor field network is basically a tensor product, between the messages, which are tensors themselves, and adding some weights. The weights can be like a learnable function, but it also has certain constraints such that it does not interfere with the equivariance. Right, so all I'm trying to say is like there's So basically, you define a new kind of operator or new kind of product, and where the product can happen between different orders and more complex data types compared to the original, like the product that we know previously, like dot product or cross product. Those are kind of restrained family of product that we define for between certain types of tensors. But here, the tensor product is really defined over like more general concept of tensors and between also like for different levels. And the irreducible tensor is just a way of simplifying, making this computation like more efficient and without breaking the equivariance. All right, so yeah, don't worry about the understanding of the full. Like, this is just giving like kind of one example of equivariance. But as we move to the like the AlphaFold type of architecture, we will see that there are also other ways of defining equivariance. But I think it's good if you working with like general geometries, right? Like 3D point cloud or like small molecules or like more random kind of point cloud that has geometry and geometric measurement. These kind of baked in equivariance will be the only solution that you can apply to the system. Cool. And also I forgot to mention about some additional rules on top of these tensor functions that produce tensors. So we talk about multiplications. Multiplications can be done freely between different tensors and with the Schurz-Gordon rules. But the linear mixing cannot be done across different types. So the linear mixing has to happen within the same type. So you can only do because linear combination is kind of very common in neural networks. So when you design these linear layers, you should be careful that it only happens between same type of tensors. And again, like Simon mentioned, the nonlinearities, you cannot apply values which break the symmetric properties with respect to the group actions. And so instead, we usually apply these gate functions, which are kind of like a element-wise multiplication. So like the sigmoid nonlinearity is applied to the invariant part, and we just kind of do like element-wise multiplication with equivariant polynomial part. So this, you will see the gating function appearing a lot in the architecture that involves like mixing up invariant part with the geometric part, and the gating function is written as a small circle in the middle. So you will see these operations a lot in either message passing or the other like IPA kind of network. All right, so now let's talk about protein folding. So we see this picture many times. Like there's a central dogma where the protein, the actual functioning proteins are these kind of molecules realized in the 3D space. We call it 3D protein structures. But the determinant of that 3D structures is the amino acid sequence, which are actually determined in the upstream by the DNA sequence, which both of them we'll talk a lot about in previous lectures in the semesters, right? So we believe that the kind of the protein folding problems can be thought of as this kind of traversing of the energy landscape of different conformation in the 3D space, given the same, this is again given the same sequence, right? So because of the different forces that's applied between the atoms in the protein, different shapes will result in this different energy, and therefore in this it can define different 3D shape of the same protein will define an energy landscape, where we believe that the folding problem is to find the optimum or minimum in this energy well that will stay more stable, such that the protein will remain in this state for a longer time because it's a very deep energy well and it's really hard to move back to the unfolded state. So this landscape is really complex. It involves a lot of like higher order interactions, and therefore, but the only thing we know is that as long as you know the sequence, it inherently determines this landscape, and therefore we know that there should be at least some like one-to-one mapping if we consider like a supervised learning task, or at least like a sequence to energy landscape mapping, and which is what we try to learn either with like more kind of a simulation-based methods or empirical-based methods or a learning-based method. So just to revisit this concept, protein is like strings of or beams of amino acid units, and we have 20 different amino acid units. Part of these different amino acid type are shared, which is the C alpha, which is this C alpha CON part, and the part that's varied from amino acid to amino acid is this R group or side chain group. And we know that the properties of the different amino acid is kind of determined by this R group, where you could have different types like polar amino acid, nonpolar, and like hydrophobic. So we know that these proteins are strings of amino acid, and there's a particular way of that these amino acid come together, combine into a string by forming this peptide bound. So for each single protein, there's a unique backbone, which is the string that's connecting the C alpha C N along this peptide bound where this polymer is formed. So we call this stream of NC alpha C the backbone of the protein. And we call this R group or the conformation of the R group like side chains, because these are like much shorter chains that are kind of stacking out of the protein like a tree, right? You have like a main stream in the middle, and you have these side chains diagonally around on the two sides. So before we talk about geometry of a structure of a protein, we can revisit the structure of a molecule, like any molecule, right? So you can consider like molecule being defined as the coordinate of each atom in this molecule. This is one way of representing the group. However, you can see that this is a very high-dimensional, like very highly variable landscape. Alternatively, you could choose a different way of representing these structures by defining the distances and angles. And there are particularly two types of angles. The one is we call bond angles, which is kind of like this for three consecutive atoms, each two of them connect with the bond. You kind of have this angles that lay in the same kind of plane. So we call this kind of bond angles. And then the bond length is just distance between a connected two atoms where a bond exists. And another type of angle is called dihedral angle, which basically it can be uniquely defined by four atoms where so you can consider like three of them forms a plane and the other three forms another plane, and you can rotate these two groups of atoms such that the angles, you have like a different angle between these two planes, so that's why we call it dihedral. So these two types of angles and bond can also be described to uniquely define a 3D geometry. All right, so you can see that this geometry of the atoms determined by the bond is very important because it also determines some forces.
If we know all the bond lengths, angles, and torsion angles, so we can uniquely.
Yes.
We have a unique molecule.
Yes, we have a unique conformation. Yes, that's so the other sets of kind of degree of freedom that you need to describe of a molecule.
So include like chirality can be described by these three things. Chirality of small molecules.
Yes, I think they should specify all the needed degree of freedom. Yeah. So so this geometry defines these geometries are important not only because they represent the 3D structures, but also they also give us information about the forces that are applied behind, in between these atoms. So, which will be important in predicting the protein structures, not for example any like structures, because these are the bounded forces that are one of the strongest forces that kind of relate things together and shape this energy landscape. So like each of these three like bond lengths and two bond angles will have corresponding kind of energy associated with them. And therefore like the geometry of, like the bound geometry of the molecule is important, and it's also uniquely related to determining the energy landscape of the molecule. But there are additional forces that can shape the energy landscape besides just the bounded forces. Particularly, for example, you can have these electrostatic interactions, because in the side chains you also have these charges. So there are electrostatic interactions that also change the energy, and these van der Waals interactions between like the atoms, not regardless of whether there's a bound, usually is kind of repulsive and attractive. So basically, things cannot get too close. You call it clash, right? They cannot touch each other. You will get a really strong repulsive force to basically break them apart. And there's like a really weak attractive force that just try to hold things together. And there's also hydrogen bonds, which also usually sometimes involves the water atoms. But these kind of, they're not like real chemical bound like the covalent bonds, but they're kind of weak interactions between like hydrogen and oxygens that can also give a slight like energy changes. And this hydrogen bond is actually very important when determining the 3D conformations of protein as well. And so usually we don't model the water molecules when making these predictions, but we kind of assume that this conformations exist in certain type of solvent. Usually the solvent is water, and therefore the observed conformation already kind of reflect the constraints from hydrogen bonding and hydrophobicity of the amino acid. This is the example I showed in the very beginning of the course, where you, if you have these beams of amino acids, some of them are hydrophobic, that are like water, the oil-like, or they're kind of afraid of waters, and the blue ones are hydrophilic, and you put them into the water, there will be this kind of forces that like apply to the entire conformation, such that at the end they kind of shape the 3D structures of the amino acid, the protein peptides. So all of these complex forces combined together, and some like unknown, maybe physics that are not discovered yet, will shape the conformation of the protein. So such that when you try to approach this problem, you can think about really, really rigid way of doing this. If you could simulate all of the forces that I mentioned, right? If you know all of this, the coordinates of everything, and you know all the solvents, all the environment, one particular way of solving this problem is just to do simulations. I just simulate these forces, and I just apply them to perturb my conformation, and at the end I can reach a place where the energy is very good. And that's exactly how people will try to approach this problem through a non-machine learning approach. And there are also different way of defining and simulating these forces, and depending on like how accurate you want to do the simulation, there's also different complexity involved in this process. Okay, any questions so far? Cool. So yeah, so we talk about structures, but actually there you could actually break down the structures into different levels, where we call the sequence is the primary structure, or like 1D structures, and we could also define the subunits of structures as like secondary structures. So if we look at everything in the 3D space, then we start to have these tertiary structures, or even quaternary structures, which usually means like assembly of different chains or different subunit. And very popular, commonly seen secondary structures, including alpha helix and beta sheets. So these are the very stable, structure that we can observe because of this hydrogen bond that appearing within these amino acid group, such that so for amino acid there are certain types of sequence of amino acid where it's very likely to form this periodical and stable like hydrogen bonding, such that it will wrap the sequence in this kind of helical fashion. And this is what we observe a lot in very solid and kind of rigid protein structures. And beta sheet is another type of kind of very stable structures where either you kind of having, again, like hydrogen bonding, that kind of lay out things in kind of a plane, and basically have this parallel strain or chain of amino acid polypeptides. And because it's parallel, you can have the parallel facing the same direction or the opposite direction. So that's why when you visualize this beta strand, you have this kind of the direction that's pointing at the whether this is parallel or anti-parallel strands. And there's also so we wouldn't say this is like a common pattern, but this is kind of everything besides alpha helix and beta sheet. Of course, there are some like complex structures that cannot be categorized into either of them, but there's very commonly seen types with this kind of very loose kind of thread. We call this loop structures, which usually are connecting these very rigid structures like alpha helix and beta sheet. So you can consider protein as like a composition of these kind of very rigid parts like alpha helix, beta sheet, and this very flexible part that's just staggering out and connecting like different rigid subunits together. All right, so this is how you can see, maybe if you try to visualize a PDB, which is the data format for protein. Originally, they should be like, you have the coordinate of each of the atoms and some bond angles, but some bound information. But to be able to visualize things more easily, we have the software that will try to recognize these highly repetitive patterns, and therefore we can have this nice visualization of protein. So when you see this kind of structures, like, yeah, there's a helix here, there's a beta sheet here, and there's a loop here. But the actual protein does not look like this. There's this still very, basically a cloud of atoms. And this is just for visualization. All right, so now let's talk about the geometry of protein. So that we know that the geometry of molecule involves this dihedral angles, right, and bond angles. So because in the protein, we can define, we know that there are highly repetitive unit of these amino acid blocks. So we're able to define the backbone. And therefore, for each amino acid, we will define the backbone atom, which is the C alpha, N, and C. Right, and so we can imagine that the positions of C alpha and N and C relative to C alpha determines kind of this local bond angle of the three atoms, right? And then there are two dihedral angles or torsion angles that are involved here. We call it psi angle and phi angle, which are basically how you rotate the bond that between the C alpha and nitrogen and the C alpha and the other carbon. So these two dihedral angles uniquely defines the degree of freedom that's involved in the polypeptide protein. So we can imagine describing the structure of the backbone with the positional information of C alpha and N and C, like the distances, and the dihedral angle phi and psi. And these sets of information is uniquely defining kind of the backbone geometry. And that's what we try to model and predict, what we try to model with the neural network or traditional method. Note that we not only consider the backbone geometry, but there's also sidechain, which are important if we consider atom-atom interactions, because backbones only kind of give you the broader scaffold of the protein, but the actual interactions, a lot of them happens with the sidechain functional group, right? But the sidechains also small molecules, right? They have, again, their own degree of freedom, such that you cannot determine the degree of freedom of sidechain by just knowing the bond angle, the dihedral angles in the backbone. So in order to represent the whole protein in all atom level, we need to additionally model these sidechain torsion angles. So we know that kind of longest sidechain will involve 4 torsion angles. So we need to memorize, basically learn at most up to 4 additional torsion angles to be able to model these structures in all atom fashion. And you can see that one thing that I kind of abbreviate here is the bond length. So in the protein folding, most of the time we can assume some rigid body, kind of local rigid body operations, such that we don't need to worry too much about bond lengths. We believe that with the angles and the positions of the major atoms, we already know the distribution of bond lengths, or a lot of time the value of the bond lengths, and we just need to put the right atom based on the position and the rotations that I defined. So assuming that the bond length is already known, because this highly repetitive small molecule unit has a pretty fixed set of bond lengths, so we don't need to remember the coordinate information of every atoms, and instead we assume that bond length is known, right? And we just need to memorize the position of some of these atoms and the dihedral angles. So with a small set of combination of these degree of freedoms, we'll be able to represent like the bigger protein all atom information, right? So assuming that you want to memorize all of this information in the 3D space, right? Then you have 3 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like you need to have 30 values to memorize all of them. But right now, what we need is just the C alpha coordinates, which is 3 values, and a set of angles, which are like 2 angles here and 4 angles here, right? So we basically represent all the degrees of freedom that is needed to determine the 3D structures, but using much smaller sets of features. We can just call it features. I mean, these are kind of the geometric quantities that we need to uniquely define the proteins. And another thing you can know is that these angles are defined in kind of in the local system, as long as you know where, if your origin is in C alpha and you have kind of one direction that you define as like basis for this is the angle 0, you can define all of this thing locally with respect to that local coordinate system. And between the 2 different C alpha and C, you can also see the relative positions between these 2 systems. So if you can manage your local orientation pretty well, then you can consider that you could use the information in the local system and just consider this part, the operation that you learn on this local system can be transformed into another local system, right? So then you could define the geometries based on the local coordinate, what we call local frames later, and just learn the kind of global information by kind of transforming making the same transformation at each different local system in the protein. So this is kind of what the assumption we made called rigid body assumptions, but it's basically, like I said, instead of modeling everything as coordinates, we have assumption that the C alpha, C, and N, the 3 atoms, can be treated as kind of a rigid body, such that the bond angle and bond length are already fixed. So as long as I know where my C alpha is and the orientation of this triangle plane, we will uniquely identify the position of C and N. So we don't need to carry the information along all of these bonds anymore. So we just break each of these amino acids into these rigid bodies of triangles. And we can now break all the bonds and just treat the protein structure as a point cloud, where each point in a point cloud is a 3D rigid body. And that rigid body not only has a point, like in point cloud you don't have kind of orientations in mind sometimes, but for this rigid body, so you do have orientations. So each 3D rigid body in this gas or cloud has a 3D coordinate and an orientation. And the problem of learning the structures becomes now learning the translations and rotations, but the positions and orientations of these small triangles. Any particular questions right now? the relative position of C and N change with respect to C alpha?
Yeah, so it's like, for the middle triangle,
Mm-hmm.
I can use this kind of vector to describe the orientation.
Mm-hmm.
But what if the C and the N changed?
You mean flipped?
Triangle, but what kind of orientation vector should we use?
So one thing I think I mentioned earlier that the sequence of protein has directions because the peptide bond can only form from C to N. So we have the notion of N terminal and C terminal, right? So basically, when we determine the orientations, you exactly what we need to model these local frames. Basically, for each triangle, we have a unique way of determining the center of mass, which is the 0 coordinate, and the XYZ or IJK direction based on this plane. And we can define it uniquely because we know the N and C are the different orientations, and we can define basically a coordinate system, which we can contrast that coordinate system with another coordinate system to get their relative rotations, or we can contrast that with the global system to get their definite rotations. So this is kind of the introduction of the local frame or like a local coordinate system, such that because this is repeated for a different unit, you can use it to either describe the relative translation rotations between two consecutive frames, or you could also define a global system, where each of them has a kind of unique translation rotation determined. And that's why that's what basically the central idea of IPA or invariant point of attention is to kind of learn the translation rotation, to learn the invariant representations that reflects local relative information and make that representation invariant with respect to translation rotations of the global frame. And then when you learn that information, you can predict perturbations to the local system. So for each of these frames, now you can add that perturbation to your local system, and then you just directly map it back to the global system because you know where each of these are at the beginning of the cycle, like in the global system. And this operation is invariant to the global system rotations and is equivariant when you map it, when you make this kind of invariant operation to the local frames and map it back to the global frame. And then you can see that each of the triangle will also have these side chains which dangling out of the frames, where we still need to model side chain with these additional phi, psi angles. But in short, because our capability to define this rigid body frame and the good, nice property that these frames are kind of, you could easily translate one local system to another system and translate that to the global system. These two translation rotation can be composite, such that you can preserve the equivariant information by adding the locally invariant operations back to the global system. Okay, any questions so far? So yeah, I think maybe maybe it's easier to understand when we look into the architecture, right? So now let's move to the architecture part. So this is the overall framework of AlphaFold 2, and next week we're going to talk about AlphaFold 3. But so basically we actually the whole architectures has a lot of very important inductive bias from the data it used to the transformer attention it used to the structure module it used. So to start with, we kind of repeatedly talk about this coevolutionary information in earlier of our course, right? So because we only have so much limited data on structures, but we have a lot of information about evolution, basic sequence data. One natural way to boost our predictions on a given new sequence is to see what nature has made in the past and see if there are certain interaction patterns that are preserved in the evolutionary trajectory. And one such common pattern is called coevolution. Basically, if two residues are contacting, they also to be able to keep the same interaction, if one place mutate, the other place should mutate accordingly. So this is what we observe called co-evolution, and we described the multi-sequence alignment earlier in our class. Basically, for any query sequence, you can look for homologies, basically retrieve sequences that are close to the sequence, and you can align them together to see what nature does to make this sequence, like what kind of mutation or deletion, insertion, or gaps that you need to introduce in the set of sequences. And we can look at the common patterns across the column and across different columns. So we can identify these co-evolutionary information. And we know that these pairs of residues that are co-evolving is highly likely to define the one-hop neighborhood, basically the contacting residues. And that's exactly what motivates the use of multiple sequence alignment as the input to the AlphaFold framework. So instead of just using the sequence that we query, we search the databases for sequences that are relevant to the sequence, and we apply the alignment algorithm that give us this MSAs. And we also search the structured database to give you some templates to be used for the sequence. So this the structured database, I mean, the homology is still based on sequence in some sense, but this is a database that you have the 3D sequence available, so that's why you get the templates on the 3D space. So this is additional, and sometimes, a lot of time, AlphaFold does not rely on the template. Even if you cannot find the 3D templates, the MSA usually contains a lot of information about this contact map. Right, so with this MSA, AlphaFold has this evil former. AlphaFold 2 specifically has this deep blocks of evil formers which process the pairwise information across two different residues in the protein. And this, why we do this pairwise information is we mentioned earlier, right? If two things are contacting, then you basically have information about two pairs of residues in the protein sequences, and that pairwise information already define adjacency matrix that somewhat reflect the structure. It is also something we call contact map. And we know that multiple sequence alignment has good amount of information about contact map. So that's why we introduce this evil former, where we apply the neural networks to look for this pairwise correlation between different residues, looking at the data. And finally, we pass on this information, basically a coarse-grained, contact map with some distance information into a structure module, where the structure module try to reconstruct the 3D space information from the 2D space information. And they use a trick called recycling, basically because it's too hard to predict something accurately just with one shot, because at the beginning you basically are shooting in the dark. You begin with some really naive guess. So the goal here is to kind of repeat this process multiple times, such that each time you're starting with a better guess, and you just try to improve that guess with another round of prediction. And you can do this for multiple times, and this is what we call recycling. And you can see that this recycling looks a little bit like diffusion, because you can think about the diffusion process as kind of gradually removing the noise, right? You're starting from completely noise, and you gradually remove the noise towards the target, such as with multiple steps, you're gradually reconstructing your structure. And but by this time, like 2021, we don't have diffusion applied to protein yet, but you can see that this recycling trick has been already used at that time to do this basically breaking down a one-step prediction problem into multi-step iterative prediction problems. Okay, so in addition to predicting the structures, they also train the network to predict the error that the network make. This is a little bit different from the kind of uncertainty model uncertainty that we mentioned earlier. But there are certain architecture for uncertainty quantification that directly predict the uncertainty. And this is one of such architecture where basically for each training data, you know the target that you apply your loss to regress into, but when you make the prediction, you can also know how far away you are from the ground truth. So in addition to just regress with respect to the ground truth, we did additional head that make these additional predictions or regression with respect to the error that you observed. basically this is saying that, like, even though I'm not able to know what the truth is at this point, but I know that I will be uncertain. Right, so it's sometimes easier to predict that uncertainties, like, but it's harder to know the correct answer, but you're still able to like say, yeah, I'm now quite out of distribution, so I should just put a high uncertainty to it. So therefore, they're a very important output from AlphaFold, where people use heavily to approximate the confidence of your predicted structure folding, which is called PLDDT, where LDDT is kind of a measurement of the error you're making at each residue. And alternatively, you can also measure the pairwise distance error, because for example, for interface, right, you really care about the whole interface, the docking of the two interface, so you really care about each pair of positions are positioned predicted correctly. So there is also a pairwise version of the error predictions, which is called PAE. So the model is trained with these additional heads that predict these values from the output of the neural network embeddings. Okay, so now let's move to each of these blocks. So the uniform block, we actually talked about it already in earlier of our class, which it starts from pre-processing the MSA information by trying to extract the column-wise, co-evolution information. And to do that, we apply XO attention, which requires a row-wise attention and a column-wise attention, and some nonlinear transitions. So after extracting these propagating information in the column-wise and row-wise manner, we conduct this outer product mean. Basically, for each position, between each position, we have like two representations, and we do outer product means that we try to now map from the sets of lengths of R sequence representation to a R by R pairwise representation. And that's what this outer product mean is giving us. Basically, it's aggregating for every pair of positions in MSA representation. We can aggregate their statistical, you do the outer product between every pairs of the positions, and you kind of aggregate a little bit like the co-evolution information or covariance information that you observed in this MSA representation that gives you this pair representation. And then it's followed by what we call triangle update and triangle attention that further update these pair representations, which are the initial guess of contact map that we got from raw MSA. But with this further triangle updates, we're kind of propagating these informations for every triplets of the points, such that kind of filling in the distance matrix beyond like contact map. So the XO attention is very similar to what we talked about early in the class. The only difference is in this kind of row-wise attention, it applies this pair bias, which it takes this pair representation and collapse it and try to use it as a bias to basically to combine it with after the dot product to give you kind of additional like bias that you already know about different positions, because in this row-wise So for in this row-wise attention, you have this pair bias coming from the pair representation as well, instead of only doing it within the MSA information. So after these two XO attentions, like I said, we apply these triangle update and triangular attention, which are the type of attention that's introduced with baked-in geometry, trigonometry constraints. So particularly for trigonometry constraints, we mean like for every 3 points in our protein, the distance between each pair of them has to fulfill the triangle inequality, right? So the distance of the two edge has to be larger than the third edge. And this triangle update is a way of doing message, kind of like message passing, but instead of only passing information to the neighbor, it considers a triplet. So every triplet in this graph So when it's gathering information, it tries to also make use of all 3 edges in this graph. So if you recall,
by distance, do you mean like spatial distance or like distance between the embeddings and the
distance between the embeddings. But these embeddings are, these embeddings will be later directly used to update the spatial tensors. So that's why it's, even though it's not in the geometry space yet, but we still want to preserve some like inequality here. So in the future, when you use these embeddings to predict the geometric features, they already give you certain guarantees. Right, so this triangle update is just for every, so in the normal graph update, you just grab information from the neighbor, but instead of just grabbing from that neighbor, you also have the neighbor of the neighbor, basically to the entire rows to give you information when you try to get information or aggregate information from each of the neighbors. So if this reminds you of, I mean, we talk about kind of the body order thing when we talk about in invariant graph neural networks. It's kind of a little bit like having like a higher body order information when we do message passing, but it's on the fly. It's not like pre-computed. And so the triangle attention is another way of injecting the inductive bias into this the attention, which explicitly give you these triangular inequality constraints. So what it does is, again, the attention, usually attention you consider like 2 points, but here it kind of consider 2 edges, which involves 3 points. And when you do the key queries within the 2 edges, you also have the 3rd edge in this triangle as the bias added to your attention, right? So you're doing like edge level attention because we're already dealing with this pair representation, right? So every entry in the pair representation is a node or kind of is an entry in the input to your attention. So that's why it looks a little bit different from the 1D attention. You see like it's only I and J, and here is I, J, J, K. But addition to these key query multiplication, you add this additional bias term coming from the third edge. So you can rewrite this form such that it will be equal to the cosine, the dot product is the distance times the cosine, and you can turn that into trigonometry. It equals to the sum of the square of the 2 edges minus the 3rd edges. And therefore, this attention here is only maximized if if you don't break the triangular inequality. If you break it, then this bias term will act and take effect, and you cancel out. So we'll have a smaller attention value. So basically, you baked in this trigonometry into this attention already, such that anything that violated the triangle inequality will kind of get downweighted, and you try to make corrections of that information by upweighting things that are geometries that are correct, and you also applying this kind of gating operators as kind of a nonlinearity. All right, so now let's move to the structure module, which is the key part of the equivariance, where the equivariance come from. So up to now, we don't deal with geometry at all. We just have these representations which reflects the likelihood of something that's correlated or not, and we have this triangle attention that kind of try to mimic the geometry, but it's not exactly geometry yet, because these are just features derived from MSAs, right, and templates. It does not have any notion of frames or orientations yet, although they implicitly inherit some of these constraints. But with the structure module, this is the first time we now directly deal with geometric features, which are, like I said, translations and rotations. Basically, the rotation will be represented by a 3x3 tensor, and that slightly different than like the spherical tensors, but there's a way of turning rotations into this 3x3 tensor representations, and translations 1x3 vectorial tensor, and we have these entire operation translation rotation as T, noted by T. So now we have the single representation, which I forgot to mention that actually besides just the evil former, there's also a single representation model that directly come from the aggregated information from pairs and the sequence itself. So you get a 1D track, which is the single representation, which kind of like collapsed version of the pair representation and the sequence itself. And you have these pair representations. So these two are scalar features. They're not geometric features. And the backbone frames are geometric features. So you have these tensors. And now the IPA module conduct a special type of attention such that it takes in the geometric tensor and scalar tensors and mix them together in SC3 invariant way, such that at the end for each of the frame, you get an embedding out of this IPA module, which is not geometric tensors. Again, it's embeddings, so it's embedding in, embedding out. Like, so scalar representation in, scalar representation out. But the scalar representation carries enough information about the relative positions or relative geometries between each frames, such that it's enough to tell, the information in this single representation, updated representation, is enough to tell you how you want to update each of this frame locally. So with this invariant representation updates, you get a prediction module here that predicts, now that I update my single representation, how should I update each of these local frames? And you apply this change back to each of the frame, and then you map it back to the global coordinate system, such that at the end, you kind of modify the structure predictions as a whole. So this part is invariant. It's called invariant point attention. It's invariant to global translation rotations of these backbone frames. And this part, this prediction of the next, of the new backbone frames are equivariant because you add these invariant operations to the global coordinate system, which changes as you apply global translation notations. All right, so this is the IPA module. So I only have 1 minute left, so I will broadly talk about it. So it looks big, but on the top, so